Hopefully this video clears up a little bit in regards to sensitivity, specificity, and the limitations in using those metrics for clinical use of diagnostic testing. So we're going to talk about sensitivity, specificity, predictive values, and likelihood ratios. And I'm going to use the two examples that I'm going to use here for this short little video are not sports rehab related or physiotherapy related. They're going to be medically related. And I'm doing that. We're picking two conditions, HIV and breast cancer. And I'm doing that because I want to give examples that are cleaner, essentially. Diagnoses that don't just necessarily run their course, as in, you don't just say if you have HIV, all right, well, let's just let natural history do its thing. This thing will go away on its own, that type of thing. You don't really do that with HIV because it's progressive, and the same with cancer. And also that we have specific, like the diagnosis means something. It drives treatment strategies. So I want to give examples of those to illustrate the points and the usage of statistics. This is not a conversation of going to the rehab diagnoses. Are those diagnoses meaningful? This demonstration is to explain the statistics of these diagnostic tests so that then you can go to our rehab tests and know why they're shit, or be able to apply these principles to those that are useful, and then those that aren't useful, but you can know why. So we're going to use the population is going to be the country of Swaziland, and the data is coming from this link here. Essentially, we're looking at a test called the ELISA test that tests for HIV. And this is real data, and I've got a table here, and basically we're just going to recreate the table here to show you what all these numbers mean. So we've got N, which is we're just going to make up a sample size, sensitivity, specificity, prevalence, positive predictive value, negative predictive value, positive likelihood ratio, and negative likelihood ratio. So the sensitivity of the ELISA test is 0.997. So what does that mean? What does sensitivity mean? Well, sensitivity is the probability of a positive test, and we'll say test positive, given, that's what that straight up and down line means. It means given that they have the disease. So we're going to make this a little smaller. Maybe make it like that. So sensitivity is the probability. What is that little deal there? Sensitivity is the probability of a positive test, a clinical test, given that they have the disease. So how do you know that they have the disease? Well, you're comparing it to whatever reference or gold standard test there is. And that's how you compare the clinical test. You compare the clinical test with the reference of the gold standard. So in rehab, a lot of times it's imaging. But the sensitivity of an ELISA test is 0.997 or 99.7%. What that means is in 100 people who actually have the diagnosis of HIV or actually have the disease of HIV, this test is going to pick up 99.7% of them. It's very sensitive. So let's say we have an N of 10,000, and we have a prevalence of 0.272. And that's actually true. That data is coming from this link right here. So in the country of Swaziland, if you just randomly sample 10,000 people, 27.2% of those people are going to actually have HIV. It's the highest rate in the world. So our N is 10,000. If you see a table like this, prevalence, which means positive tests of the gold standard, so those who actually have the disease, out of 10,000 people, the prevalence is 27.2%, so that means that 2,720 people are actually going to have the disease. So if the sensitivity is 99.7%, meaning that this ELISA test is going to come up positive in 99.7% of the people who actually have the disease, that means this block right here needs to be the number of true positives for the test. So that's going to be 99.7% of this number of the prevalence. So if we did 20 times 20 times 0.997, that's about 2,712. And then this number here, false negatives, the ELISA test negative in the people who actually have the disease, would just be the difference. So that would be 8. So out of 2,720 people who actually have the disease, the ELISA test is going to pick up 2,712 of them. It also has a specificity of 92.6%. So what's specificity? Specificity equals the probability of testing negative given no disease, or disease negative. Or in other words, specificity is our true negative rate, whereas sensitivity is our true positive rate. So we know, first of all, if there's 10,000 people and 2,720 of them have the disease, well, that means the difference between those two numbers of people don't. So 10,000 of our sample minus the 2,720 that have the disease means that 7,280 don't have the disease. And that's what we have up here. Now, of those who actually don't have the disease, according to the gold standard test, we know that our true negative rate for the ELISA test, aka specificity, is 92.6%. So in this box, our true negatives, and negatives with the ELISA test, negative for the gold standard, that needs to be 92.6% of this number, all of those who actually don't have the disease, which is 6741. And then this box is our false positives. So this is people who don't actually have HIV, but tested positive in the ELISA test. And we get that number simply by finding the difference between these two. So 539 false positives. So that's what, and then we just add across here for this total. 3251, add across here, 6749. This adds up to 10,000. Had to make sure there. This adds up to 10,000. And this is what it would look like for a test that's 99.7% sensitive and 92.6% specific. This is what the 2x2 table would look like. Now, here's the problem with sensitivity and specificity. These numbers look pretty good, right? 99.7 specific, 92.6, 0.997 sensitivity, 0.926 specificity. That looks pretty good. The issue is sensitivity and specificity, number one, they're dichotomous. You know, spin and snout, we think, okay, rule in, rule out when we have a positive or a negative test. But we know that these tests are not perfect. So even with this test here, that looks pretty good, but this is not one. This is not one. So we know that we're going to have some false positives and that we're going to have some false negatives. So not everybody who tests positive on this test, the ELISA test, actually has the disease. Not everyone that tests negative on this ELISA test is clean. So we can't dichotomize these things. It's more about probability. So that's number one. And number two is sensitivity and specificity are happening in the opposite order that we have it in clinic. This sensitivity is the probability of a positive test result given that we know they have HIV. But in the clinic, we don't know they have HIV. That's why we're testing them. Or we don't know that they have the condition. That's why we're testing them. We know that they have or don't have the condition here because we're comparing it to a gold standard. We already have that information. So sensitivity and specificity are just a step to start to appraise the diagnostic utility of a test. It doesn't stop there when we're trying to find the diagnostic utility of a test in clinic. What we actually want to know is the opposite of this. We want to know the probability of the disease given the test result. So we're in clinic, we do a test, we get a positive or a negative. We want to know then, based on this positive or negative result, what's the probability of disease? So we actually want to know the opposite of what sensitivity and specificity are telling us from that regard. And we do that with predictive values. So predictive values are just that. They are the probability of the condition given the test result, which is what happens clinically. So a positive predictive value is the probability of having the disease given a positive test. A negative predictive value is the probability, I don't know why it's bold, is the probability of not having the disease given a negative test. So you test negative in the clinic, you want to know then what's the actual chance that I'm clean. You test positive in the clinic, you want to know, okay, I tested positive, but what's the probability that I actually have the disease then? That's what we want to know, and that's what predictive values give us. And predictive values are given or are calculated here. So if you have the sensitivity and the specificity and you have the prevalence data, you can calculate these numbers. And for us, if we have a chart like this, we can actually calculate these numbers really quickly if we have a box like this with all these numbers. Because a positive predictive value is simply this number over, which is our true positives, over the total positives for that test. So 2712 divided by 3251, and that gives us a positive predictive value of 0.83 for the ELISA test. So that means that if you test positive in the clinic, if you test positive for the ELISA test, there's an 83% chance that you have HIV. So we get sensitivity and specificity by going down the columns and we get predictive values by going across the columns. A negative predictive value, if we use this box over here, can be calculated by our true negative rate, which is this number here, over total negatives of the ELISA test. So 6741 over 6749. And that gives us a negative predictive value of 0.999. So that means that if you go in the clinic and you take the ELISA test and it's negative, there's a 99.9% chance that you're clean. So that seems pretty good, right? So basically what happens is we have a prior probability of the condition, or the prevalence, before we test. And if we know that, that's awesome. Whoops. Likelihood ratios aren't supposed to come up. That's a secret. So our prior probability in this case is our prevalence, 0.272. That's our prevalence. That's before testing. You take a random person out of this population and they already have a 27.2% chance of having HIV. And we know that through the prevalence data. And hopefully that's data that you have. And if it's not, then we talk about that, because that's a problem. And that's what makes these tests a problem, when we don't have complete data. But we have our prior probability of the condition, which is our prevalence, and then we turn that into a posterior probability of the condition after testing. So our posterior probability for having the disease, if we test positive, is 0.83. So we go from a random person walking in the clinic already having a 27.2% chance of having HIV. They test positive. Now they got an 83% chance of having HIV. Random person walks into the clinic in the country of Swaziland. They already have a 27.2% chance of having HIV. They test negative. Now they've got a 99.9% chance of being clean. So, if we could just stop right there, that would be awesome, because we pretty much have everything we need. The issue is predictive values are totally dependent on prevalence data. You can see it here. The prevalence is in both sides of the equation, the numerator and the denominator, for both positive predictive values and negative predictive values. The prevalence dictates, if we took this number away, this is the prevalence, by the way, it would totally change the entire structure of this table. So if we don't have prevalence data, we can't calculate predictive values, number one. Number two, the prevalence data can only be generalized to that population. See, this is lucky here. We've got data on an entire country. But a lot of times you're going to see predictive values in a study that are only for that sample and the prevalence of that sample. That cannot be generalized to the population unless it is a representative sample of the population, unless the prevalence is the same. And a lot of times it is not. So you have to be very careful with trying to generalize predictive values beyond the study, even if you have prevalence data within the study. If it's not the exact same as the general population, you can't generalize it. So you just have to be aware of that. So then, that's where likelihood ratios come in. Because likelihood ratios are independent of disease prevalence. Likelihood ratios use sensitivity and specificity. They're essentially ratios of two probabilities. So all we need is sensitivity and specificity, and we can calculate a likelihood ratio. We don't need the initial prevalence data, which is good. It gets us another step of the way. We are going to still run into the same roadblock, and that we'll explain here in a second, but it's nice in that regard. So essentially, a likelihood ratio is the probability of getting a result, could be positive or negative, if the patient truly has the condition, over the probability of getting that same positive or negative result if the patient truly does not have the condition. So, in other words, a likelihood ratio of 1 would mean essentially that the test didn't change anything. It was meaningless. So a likelihood ratio that gets further and further to the right of 1 or greater than 1 is stronger evidence for the presence of the condition. And a likelihood ratio that gets further away and less than 1, or further to the left, or less and less than 1, is evidence for the absence of the condition. Those essentially tell us to what extent the probability of having the condition is changed after you get a test result. And you'll see positive likelihood ratios or negative likelihood ratios, and that is just referring to the result of the test. So it's a positive likelihood ratio doesn't mean that the ratio is a positive number, and a negative likelihood ratio means that the ratio is a negative number. That's not what it means. It's always, any likelihood ratio number is always equal to or greater than 0. So it's never a negative number. So a positive likelihood ratio is referring to a positive test result, and it's calculated this way with sensitivity and specificity. Or in other words, a positive likelihood ratio is the probability of a positive test in those with the disease over the probability of a positive test in those without the disease. So let's say you had a positive likelihood ratio of 10. That would mean that with a positive test, that person walks in with a certain probability of having the disease, they test positive. If that test has a likelihood ratio of 10, that would mean we now have a 10-fold increase in the odds of having the condition. So if you look over here at the ELISA test, that likelihood ratio is 13.4. So in that case, we have a 13.4-fold increase in the odds of having the condition. A negative likelihood ratio is referring to a negative test result. And that's calculated this way, which is essentially, or it is, the probability of a negative test in those with the disease over the probability of a negative test in those without the disease. So let's say a negative likelihood ratio of 0.1, for example, would mean that with a negative test, we have a 10-fold decrease in the odds of having the condition. So if any test had a negative likelihood ratio of 0.1, then that would significantly decrease the odds of somebody having the disease if they tested negative. And we see over here, the negative likelihood ratio of the ELISA test is 0.003. So that's much less than 0.1. So same idea here. So with the ELISA test, this is a pretty solid test. We don't have anything like this in rehab land. Something that gives you a super strong negative predictive value, pretty strong positive predictive value, which we can increase with 2 positive tests, which I'll show you in another example. Likelihood ratios of 13 and negative likelihood ratios of 0.003. We just don't have that in rehab land. But this is giving you a nice illustration. Now, what does, a likelihood ratio of 13, well, that doesn't mean 13%. It just means that you increase the odds 13-fold. Well, from what? What was the starting point? Because what if you're already walking in with a very, 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 very low likelihood of having the condition? Well, then in that case, this would just be 13-fold of something that's really, 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 really small that would end up still being small. So how do you figure out what your starting point was and what your ending point was? A likelihood ratio kind of gets you there. And we do that through what's called a nomogram. So this is basically us getting back to what positive predictive values and negative predictive values give us, which is prior and posterior probabilities. We can do similar things and almost the same thing. We can actually use the nomogram for positive predictive values too with likelihood ratios. So let's use this for example. The ELISA test has a likelihood ratio of 13. We have a prevalence data of 0.272, which is equivalent to pre-test probability, as in what's the probability of this person having the condition pre-testing. So if we have the prevalence data, so we'll just use that. And this is how you use a nomogram. I'm going to insert a line. Our pretest probability is 0.272, 0.2, where are you at? 0.2, 0.3, so somewhere about here-ish. And then I'm going to cut through. Our likelihood ratio is 13, so that's somewhere up here. And somewhere like that, right? And where does that put me? Post-test probability, right about there. Oh, that looks like about 0.83, does it not? Hey, that's super darn close to our positive predictive value. Well, there you go. So let's do the same thing with the negative likelihood ratio. We have a negative likelihood ratio of 0.003, which is super duper small. Our pretest probability is the same. So here is our pretest probability. I'm going to do another line. Pretest probability here, 0.272. My negative likelihood ratio is 0.003. Which is somewhere in here. So I want to cross that line. And that puts me way down here, close to 0.001 as a post-test probability to having the disease. And wouldn't you know it, wasn't our negative predictive value 0.999, which is essentially saying the same thing? Over here, I start with 27% chance of having the disease. Negative likelihood ratio takes me, with a negative test, takes me all the way down to basically 0.001 chance of having the disease. And our negative predictive value said the same thing in a different way. It said you're 99.9% likely to be clean. So that's how we can use this nomogram and likelihood ratios. And this is a Fagan nomogram. A couple things of note here. You might wonder, where the heck, how do they know where the likelihood ratio goes in the middle? How exactly do they get this relationship? You can calculate it by hand right here. You could take all of this. So we could take our pretest probability, 0.272, and we convert it to odds. We convert it to pretest odds, which is 0.272 over 1 minus itself, and that's the pretest odds. I know you're probably squirming right now, but we're just going to do this. We're just going to do it. 1 minus 0.272 equals 0.728, 0.728, 0.272 divided by 0.728. So our pretest odds, 0.374, 0.374. Then we go to the next step. We calculate our post-test odds, which is Pretest odds times likelihood ratio. So this number times a likelihood ratio. 374 times 13.47 for the positive likelihood ratio. 0.374 times 13.47. 5.04. So that's our post-test odds. Now we convert odds back to post-test probability, last step, which is the odds over 1 plus the odds. So what's that? 5.04 divided by 6.04. Oh, look at that. 0.83. Wouldn't you know it? The same thing as our positive predictive value, the same thing we got over here when we use the nomogram. So there you go. Now a couple things here. You're probably wondering, well, didn't you say that likelihood ratios are good because you don't need the prevalence data? So that's not exactly, you don't need the prevalence data to calculate the likelihood ratio. However, to create meaning to the likelihood ratio, you need some type of post-test probability. And this is where it gets really sketchy, because if you don't have prevalence data or some type of pre-test probability data, it could be a valid clinical decision rule, which we don't have very many of, validated, tried and true, that gives us some subset of symptoms, or like a test cluster, and say, okay, when you have this test cluster, you have a pretest probability of the condition, a pretest probability of whatever for the condition. So you can start there. We use the base rate here. So base rates are really, really important. They're required for positive and negative predictive values, but they help you give meaning to likelihood ratios. It gives you that starting point. Otherwise, pretest probability comes from intuition, or it comes from clinical experience. And this has been literally stated in the papers, a gestalt, almost like a gut feeling. And this is a big critique. So you just keep that in mind. This is why base rates are really, really important. And that type of information, you got to dig for it. So we run into the same problem with likelihood ratios that we did with prevalence, with positive and negative predictive values. It just took longer to get there. So that's the deal here. Now I wanted to show you guys another example, which is pretty cool, because it'll take things a step further. And this is about breast cancer and mammogram data. And this is real data that comes from these sources here. There's a lot of criticism on mammograms, and I think this illustration will show you why, potentially. But it's not that they're bad. This is just like actually real life here, or very realistic for diagnostic tests. Let's look at some of this. So sensitivity of the mammogram, 0.782, and these are estimations, by the way. Specificity, 0.9. Prevalence of breast cancer in the general population, 0.017, so 1.7%. 1.7 people out of 100. Well, that's your base rate. That's your prevalence. Look at this positive predictive value. This is why you can't let sensitivity or specificity make the decision of probability of disease, because it's not what it gives you. Because check out sensitivity and specificity. It's not great at 0.78, 0.9, but look at this positive predictive value. If you test positive in your first mammogram, you have a 12% chance of having the disease. Think about that. You come in, you have a positive mammogram. You're like, oh crap, I have breast cancer. No, actually, you have a 12% chance of having breast cancer with one positive. So that's why we can't just rely on these numbers here. Check out the negative predictive value though. If you walk in to the clinic, you're just randomly selected member of the general population. You already have a 1.7% chance of having breast cancer. That's your pre-test probability, your prior probability. Let's say you test negative. Well, now you have a 99.6% chance of not having breast cancer. So that's good. That's where the mammogram helps us. The mammogram does not help us when it's positive, at least the first one. And now check out these likelihood ratios. So positive likelihood ratio of 7.82. So let's do this here. Let's take this prevalence data, 0.017, 0.017, somewhere here, and then a positive likelihood ratio of 7.82, somewhere like right there, right? So we went from a pretest probability of having breast cancer, 1.7%. I tested positive likelihood ratio of 7.82. That takes me to a post-test probability of having breast cancer of about 12%. Sounds familiar. How about negative likelihood ratio of 0.242? So we start in the same spot, coming in with the same pretest probability, negative likelihood ratio of 0.242, which is like somewhere in here. And now that takes me down to about less than 0.5%. So it's already really low, right? I mean, you come in, you only have a 1.7% chance of having breast cancer when you walk in the clinic anyway. You get a negative test, and now it's even lower, which, again, is the same thing that this is telling us. So it took us down to about 0.004 probability, and that's basically what this is, 99.6% chance of being clean. So that's kind of an illustration of how you're using likelihood ratios. Now, what happens now with a positive predictive value of this? So what do you do with that, with a positive test? One positive test doesn't tell you anything, right? It increases. This is actually a really good example of relative increases in odds versus absolute probability. So you went from 0.07 to 0.12. That's actually like a 7-fold increase in your odds of having the disease. So if you just say it like that, wow, I had a positive mammogram, my chance of breast cancer is now 7-fold greater, which makes sense, right? Positive likelihood, 7-fold greater. That sounds really high, but it only takes you to a post-test probability of 12%. So you've got to look at both relative and absolute. So what do you do with that? Well, I want to show you something really cool that basically you can, if you got a second test, you would now have a new prior. So you tested positive first time. Now your prior becomes 0.12. Our prior was 0.017. That was our prevalence. Our pretest probability, 0.017, or our prior probability, same thing. We tested positive. Now the probability of having the condition goes up to 12%. So we start there. What would happen then if this person got a second mammogram and tested positive for the second time. Well, now let's take our pretest probability to 0.1, because that's where we are now, 0.12. Positive likelihood ratio of 7. Now we're getting up close to 50% post-test probability. So now with 2 positive mammograms, we're at about 50% chance of actually having breast cancer. That's still really frustrating, right? So I've tested positive twice. I've gone to the clinic. I've had 2 tests. They've both been positive, and it's still a coin flip. What if you got a third test? Our post-test probability of 0.5 from that last test now becomes our prior, because I'm going in for a third. 0.5 now is my pre-test probability. I have a positive likelihood ratio of 7. Where does that put me? Oh, now that puts me up closer to 0.88 or 88%, almost close to 90% post-test probability. So now it's we're getting somewhere where it's increasing the likelihood of having the condition. That's how this would look, and that's why I chose examples that don't just resolve with natural history, and that's why pain makes these so complicated. Our conditions in rehab, impingement syndrome and pain-based syndromes, patellofemoral pain, non-specific low back pain, the pain ebbs and flows. So the tests, it's hard to test for something like that. Whereas with cancer, you can come back and you can retest and retest and retest, and the condition is more stable. So you can use these numbers to update your priors. This is Bayesian inference, essentially. And you can use the Nomogram to do that. So after 3 positive tests, you can now say that the likelihood of you actually having the condition is pretty high. I want to show you guys a cool way to kind of work through these things. And you don't have to do this, but it's a nice way to solidify it. Oh, here you go. Here's one. I'm going to make a new one. Paintbrush is where all the magic happens in life. Whoop. Okay, we're going to use the mammogram data. So what do we know? We know that prevalence, prior, I'm going to just all the names, pre-test, probability, base rate equals 0.017. I know that sensitivity equals 0.782. I know specificity equals 0.9. Again, you could do this with any test. We'll say mammogram. Okay, we're going to make a tree diagram, because a lot of times what you'll be given, what data we have, for example, the probability of a positive test result given that you have the disease. What we want, probability that we have the disease given a test result. And I won't even say positive or negative, I'll just leave it here. So when we have an kind of an inverse with what we want, a tree diagram is really useful. This is basically doing what we just learned how to do by hand, but I think it's a really nice illustration on understanding these things. So we're gonna do one. We're gonna make a tree diagram to basically find the predictive values that we had already found. So we're gonna do it. Okay. A tree diagram. You guys should make one of these. Really, really helps. So yep. Okay. So we're going to call this breast cancer, and this is going to be no breast cancer, because that's what you're walking in. You got somebody walking in. They either have it or they don't. And the probability of breast cancer is our base rate, 0.017. The probability of no breast cancer is the complement of that. Complement is basically just 1 minus the other number. So that is 0.983. Each branch will add up to 1. So every level of these probabilities, these two numbers will add up to 1. Another branch over here always add up to 1. And by the way, this first level here, these are called marginal probabilities. Marginal because they come from the margins of the contingency table, this is a contingency table. These are the margins. Prevalence data comes from the margins. Okay? Now, we have conditional probabilities as the next level of the tree. So somebody comes in, they actually have breast cancer, but we have to test them. So they take a mammogram. That's either going to be positive or negative. And we know the probability of a positive test result given breast cancer, aka sensitivity, is 0.782. This is your sensitivity. Sensitivity. Boom. This is probability of negative because negative given breast cancer. So because we're on the breast cancer branch here, we're working our way across. This is also known as your false negative rate. And that is 0.22. Because these are complements. They have to add up to 1. So this person could walk into the clinic and they don't actually have breast cancer. They take a mammogram. It's either going to be positive or negative. So they don't have breast cancer. They test negative on the mammogram. So the probability of negative given no breast cancer, aka specificity, which we already know, is 0.9. Specificity. Boom. And then here, probability of testing positive, given that they don't have breast cancer, is the complement of specificity. This is also known as the false positive rate. This adds up to 1. These add up to 1. Now, this next level is going to be what's called joint probabilities. This is the probabilities of both conditions happening simultaneously. And to get these, we just multiply across the branches. So, the joint probability of breast cancer and testing positive equals 0.017 times 0.782. It's a product equals 0.013. Promise we're getting somewhere. The probability of having breast cancer and testing negative is the product of this number times this number, which is 0.0037. The probability of no breast cancer and testing positive, so I multiply these two numbers, is 0.0983. And the probability of no breast cancer and testing negative, wait, hold on. You probably caught it before I did. Okay. Now the probability of no breast cancer and testing negative is 0.885. We just multiply across. So these are joint probabilities. We've got marginal probabilities, conditional probabilities, because we've got conditions given this condition, given that condition. Positive given no breast cancer. And then we have joint probabilities of both of these happening together. Joint probabilities. So, from here, you've probably in these papers that explain positive predictive values, negative predictive values, likelihood ratios, have mentioned something called Bayesian Bayes theorem. Sorry, Bayes theorem, which is a mathematical construct that allows us to calculate conditional probabilities. And what's the conditional probability that we want? Is we want the probability of disease given a test result. So in these two cases here, Bayes theorem is, first of all, is the probability of A given B equals the joint probability of A and B divided by the probability of what you're conditioning on. So we'll just put this here. So we're going to use Bayes' theorem to get this, to get what we want, which is the probability of a condition. We're going to use Bayes' theorem for that. And we can do that because we have all of the numbers now. So the probability, what we want, the probability of breast cancer given that we had a positive test. What does that sound like? That sounds like a positive predictive value, right? Equals, according to Bayes' theorem, the joint probability of both of these things happening, which we already know. We calculated that, 0.013, divided by the probability of positive test results. So we're interested in every branch that has a positive test result. We have two of them. Positive, positive. So we have 0.013 plus 0.09883. So this, all of this equals 11. It actually equals 0.117. So, based on what we just did here, the probability of having breast cancer given a positive test result using Bayes' theorem is 0.117 or 11.7%. Well, gosh darn it, that looks a lot like the positive predictive value that we calculated over here, or that we already have. So you just did a full-on mathematical proof, not really, but sort of. You just free-handed how we got this value. Now, what if we want to know the negative predictive value, the probability of no breast cancer given a negative test? Well, using Bayes' theorem, that would equal the joint probability of no breast cancer and a negative test. So that would be this branch here, which we calculated to be this, 0.885 divided by the probability of negative conditions. So now we're interested in every branch that was negative. So we have two of them. You have this one, 0.0037, plus this one, 0.885, and that ends up being 0.996. Well, hot damn, that looks a lot like our negative predictive value that we had over here. Again, just showing you guys how you can basically do this freehand. Now, what's cool is what would you do? Because we already know that, well, gosh, this person, they had a positive mammogram, and now their posterior probability of having breast cancer is only 12%. What do we say what we would probably do is recommend another test. Well, what would you do here then? You would update your priors. So now, this tree diagram, we redo it. There's no way that any of you have stayed this long. But if you have, holy hell, what is wrong with you? Get a life. No breast cancer. Okay, this is what's different. They're walking in the clinic. They already had a mammogram. They had one. It was positive. So now, actually, they already had a mammogram. It was positive. So now their probability of having breast cancer increases to 11.7%. I'm actually going to say probability of breast cancer. Yeah, like that. Boom. Because we started with just our prevalence data because that's the only prior that we had. But now we have a different prior because this person has already got a positive test under their belt. We add that information to our prior, and their probability increased to 11.7%. So that becomes our new probability of them having breast cancer. So now the probability of them not having breast cancer is the complement of that. 1 minus 0.117, which is 0.883, which is a little bit less than what it was before, which makes sense, right? Because now their chances of having breast cancer are slowly increasing. So the probability of them not having breast cancer is going to be a little bit less. This is important because this is where people kind of trip up here. The diagnostics on the test have not changed. So this part of your tree diagram doesn't change. The sensitivity and the specificity are unchanged. So this entire level here, the conditional probabilities, is going to be the exact same. So for sake of not redoing this, we're just going to, hopefully you guys understand that. That doesn't change. What will change, though, are these joint probabilities, because this is different. We're going to multiply across, and these numbers are different, and you're going to see what it does. God, this video has turned into, I'm sorry, I'm really sorry. Okay, so we multiply across 0.117 times, again, unchanged, it'll be over here. Probability of breast cancer and a positive test, 0.091. Probability of breast cancer and a negative test, 0.0257. These are joint probabilities. We're multiplying across. Probability of no breast cancer and positive. Probability of no breast cancer and negative, 0.795. Forgot to put a number on this one. That's 0.0883. Okay. So now we do the exact same thing we did up here, down here. We want to know now, what's the probability of having breast cancer given that we have 2 positive tests? We use Bayes' theorem. It's going to be the joint probability of having breast cancer and having our second positive test. These should have positive and negative. So that is 0.091, whoop, because that's this number right here, divided by all of the conditions that are positive, which will be this branch and this branch. So 0.091 plus this one, 0.0883, that equals 0.51. So now it's exactly what we found when we did our nomogram, was it not? Positive, negative, positive, negative. So now this person has, their positive predictive value has increased. After the second mammogram, after the second positive test, they now have a posterior probability of actually having breast cancer up to 51%. Still a coin flip, still frustrating. But is that not exactly what we found when we were messing with this and we were changing our priors every time we updated? Right? So we're basically, I just showed you how to do it by hand. It's good practice to do this. I would say it's fun, but that's kind of weird. But this is called a tree diagram, and it just helps you kind of ingrain what's happening. So if you stayed this long, I don't know what's wrong with you. I'm going to throw this up into the forum, and let me know if you have